Let's wait for a few minutes, maybe one more minute, and then we will get started. Okay, we'll get started now. So, today is the fourth day in our system design series. Before starting with today's agenda, I will briefly walk through whatever we have done previously. So on the first day, we learned about the fundamentals of system design. We covered the framework of system design. So whenever you have a system design question, how do you basically start approaching the question, and what all you have to cover while answering the question is what we discussed in the first session. We also learned about whenever you have a question given at you, how do you start with the first step, which is basically understanding all the requirements of the system. You break down the requirements into a functional, non-functional requirements. After you have done that, you do a capacity estimation where you estimate the scale of the service, the scale of the data, the scale of the users, how many requests are being sent. So all of that we did in the first day. In the second day, we covered the high level design where we learned about high level building blocks of the system. So, for example, we learned about databases, caches, load balancer, content CDNs. So, a lot of different high level building blocks is what we covered on day two. And in day three, we learned about the low level design, which involved low level building blocks of the system, which involves primarily everything related to object oriented programming. We learned about design patterns. We learned about uh, with respect to object oriented programming, we learned about what are the different paradigms that we have to cover when keeping in mind when we are designing a low level building block. So we also learned about the four different types of design patterns and how to basically take that into account when answering a low level question. We also learned about solid principles. It's also a very important principle to keep in mind when you are approaching a low level question. So this was what we covered previously. If you have uh, missed out on any of those session or not been part of those sessions before, you can just go watch them after the today's session. So for today's session, the agenda is to cover the advanced topics with related to system design. These topics are not that elementary, but also these are very crucial for any system out there. Any real time system out there pretty much uses all of these topics that I'm going to discuss today. So whenever you are designing, it primarily comes under high level design, but it is not a preliminary high level design. It is a bit advanced than what we covered on day two. So we'll get started. And meanwhile, if while I'm going through the topics, if you have any questions, anytime feel free to drop in the comments. I will try to take the questions while I go, or if I miss any of it, I will take it towards the end. Okay, so first topic is distributed cache. So all of these topics that I'm going to discuss today is primarily relates to the distributed systems. So we covered the caching and databases in day two during our high level design. So this is one step further from that. So we all know why we need a cache, what cache is. Cache primarily you have a database where you store all the data, but every time you want to read and write to the database, it can be a costly operation. It can be slower. It can slow down in the entire system. So to make things a bit faster, we use a layer above the database, which is called cache, where cache basically provides us a faster access, so we can get a quicker response if you want to read and write a data. So it'll first go through the cache. If, let's say, if you're reading a data, it'll first go through the to the cache. If the data is present in the cache, it will be provided from the cache, and if it is not in the cache, then it goes to the database. So it helps saves us a time. And cache also has a lot of cache eviction policies which determine what data to store in the cache. So primarily it's most frequently used, most recently used is the data is which is in the priority, and whatever data which is least recently used and least frequently used is discarded from the cache depending upon what is the capacity of the cache. So now here you can see in the picture on the right hand side, we have multiple databases. We have, okay, let's start with the client side. So you have a client, you have a load balancer, which basically distributes the data across different databases. And so all these service, let's say there are here, we see there are three different types of service. Each of these service can have their own set of specific data. So rather than going directly to the persistence layer, which is the database, we have a cache in between just for the same reasons to provide a faster access. Now here, each of these service has access to all of these different cache servers. You can see like the first one can access any of these three, same for the second and the third one. So this is what exactly is the distributed cache, where you have not just one cache but multiple cache into the picture. Let's go through what is written here. So when the size of the data required in the cache increases, storing the entire data in one system is impractical. This is because of the following reasons. It can be a single point of failure. So if we just have one cache, it can be a single point of failure. So if the cache goes down, we will not be left with any other replica to basically quickly replicate the cache and keep the system up and running. If the cache goes down, it will have to go through the database, and meanwhile we can try to have another cache up and running. So again, it will not uh, be a scalable solution, where because if the cache goes down, you are just slowing the system. So in that case, we have to avoid the single point of failure and bring in more cache into the system. Now, the second point is a system is designed in layers, and each layer should have its caching mechanism to ensure the decoupling of sensitive data from different layers. So, also, let's say a large scale system, if we talk about an e commerce system. So, an e commerce system can have a huge scale of data. So, it can have all the inventory data, all the data related to the products that they are selling. They also have a user data, everything related to the user, their name, address, logistics, payment details, everything what they have. They also have data related to all the sellers that they have with them, like seller related, all the seller related information, plus all the products that the seller is selling. So you can imagine the scale of the data. So all this data will essentially be stored in like separate databases. So all of these databases will have their own cache, so that we are easily able to decouple the system altogether, and we just don't want all of these different types of data to be just stored in one cache, because again, we will defeat the purpose of having a cache, because if all the requests will go to just one cache, it will again slow down the system. And now the third point is caching at different locations helps reduce the serving latency of at that layer. So it's pretty much the same thing which I told you. So you don't want all the product related, all the user related, all the seller related, everything, all the data to just put in one cache. So we want to have multiple cache. Now we'll see how basically all these multiple caches come into picture. So I'll just try to explain through the diagram. It should be very easy to understand. So the first one, the one on the left, explains how a cache works, basically internals of the cache. So there is a primary cache and there are two secondary caches. So again, the secondary are just the replica of the caches. So if the primary goes down, the secondary can be the primary and it will serve the request. So inside the cache, you can see there is a map and there is a linked list like of structure. So the map basically tells you, so let's say you have a you are given a user and you have to fetch all the data related to the user. So here the key will be the username and the value in the map will be the address where that user related data is stored in the cache. So let's say if I'm searching for a user, I'll just go to the key and just find the particular address where, let's say I'm looking for key 2. So I will go directly to the key 2 index in the map and I will get the address of that key. Once I have that address, this means this will point to the address in the linked list where the data is stored. So this points to here. This means this is the data that I want. So this field will contain all the related information related to the user that I'm searching for. So this is how you fetch data from the cache. Now, why do we need a linked list like of structure? Because so you know how cache stores data based on least recently used. So whatever is ahead in the linked list is basically the data that is used most recently. So it is also a doubly linked list. So let's say towards the head of the list we have value 3, then we have 1, we have 4, we have 2. This means the value 3 is the most recently used. Then the next one is the value 1, then 4, then 2. So here the value 2 is the one that is least recently used. So let's say at any given point of time, if here the capacity of cache can store all the 4 data, so we will store all the 4. Now let's say if a new data is searched, so that will be put somewhere before the head. We can doubly linked list allows us to just go to it allows us to do a constant time search as well as insert and delete operation. So here we will just put that the new value in the first position, which will be the head of the linked list, and we will just eliminate the last one. The last one will be the one that is least recently used. So pretty much every cache uses a linked list sort of structure to keep an order of the frequency in which the data is used. So now let's say we are using value 2. We go to the address of value 2, we fetch the value. At the same time, we will just cut this linked list here and we will move value 2 first. That will mean that the value 2 is used least recently. No, sorry, value 2 is used most recently and it's no longer least recently used. So that's the point of linked list. So this is what is inside just one cache. Now we are talking about multiple caches. So the one on the right side, this shows how multiple caches work. So we have a client, we have a load balancer. This will go to these servers. Uh, I just want to quickly recap. So load balancer, if you have not watched the first, not the first days, I think I covered load balancer on the second day. So load balancer basically distributes the data across the different servers, different databases that we have in the system. So you can go back and watch the day two's agenda that will cover the load balancer if you don't know about load balancer. So now the load balancer distributes the data across multiple servers. Now you can see each of these servers. There are 3 servers, and then there are 3 caches. So we have a configuration service. So what it does is it's basically, let's say the first server needs user related data. So it'll first go to the configuration service. This service will tell the server which of the caches store the user related data. So let's say this will tell the second cache stores all the user related data. So now this application server will go to the second cache. Now here, each of these internals will be same as this, what we studied here. So basically there's an extra layer of configuration mechanism which will point to exactly which cache to access, and then the server can go and access that cache. So there is also a monitoring service which will basically tell the performance of the cache. So as we have like we discussed here, we have a primary cache and we have a secondary cache. So this is the same thing that is shown here. So we also want to quickly, not on a real time basis, monitor all the caches. So let's say if the primary goes down, we want to quickly catch it and have the secondary take the place of primary. So that's what the monitoring service does. It keeps a health check of all these different caches, and it just quickly monitors on a real time basis which of the cache is up and running, and if any of the caches go down, it will alert the system and the secondary cache can take the place of primary. So that is the monitoring service. So this is the overall architecture of a distributed caching system. So this is all about caching. Now let's move on to the next topic. So it's about rate limiter. Rate limiter is, I would say, it's one of the most important topics in a distributed system. It's pretty much used in any part of the system. It can be used on the server side, it can be used on the client side, it can be used on the database side. It's pretty much used anywhere in the system. So, what exactly it does? So, a rate limiter puts a limit on the number of requests a service can fulfill. Um, the second point is a rate limiter is generally used as a defensive layer for services to avoid excessive usage, whether intended or unintended. It also protects services against abusive behaviors that target the application layer, such as DOS attacks and brute force password attempts. So, for example, let's take an example. If there is a hacker who wants to hack a system, so for hacking, one of the types of attacks can be a DOS attack, which what happens is the hacker sends huge number of requests to the system at a given point of time. So let's say if your system can handle 100 requests per second, and the hacker sends they use the automated system and they send, let's say, 10,000 requests to your system. So your system won't be able to handle, and it will just deny service at that time. Your system will go down. So to prevent such kind of mishaps, what is done is we have a rate limiter which basically controls the number of request that reaches your system. So it will be a layer before the system, and that will control. In our case, if the 100 is the limit of the number of requests a system can handle, so when it goes up anything more than 100, it will just not send the request to the server. It will just discard all the requests even before reaching the server. So this is what the rate limiter does. Now, below are the few scenarios where a rate limiter is it's highly used. So first is preventing resource starvation. So this is the same which I told you. So if there are 100 requests, 100 is the capacity of the server. We don't want to send anything more than that because that will just starve our resources. So whatever resources we have in a system will only be able to handle 100 requests. So if you remember in our day one, we discussed about capacity estimation. So there before even we start designing the system, we try to understand what's the capacity that we want the system to handle. So that in that amount of time we understand, let's say, if how many users we want in the system, how many requests we want in the system. So that serves as a preliminary criteria for designing the system. So if we have kept 100 requests in mind for designing the system, so if anything above 100, the system will just starve and it will just go down. So rate limiter will keep the system up and running, and even if there are more than 100 attacks, it will just discard anything more than 100. The second one is managing policies and quotas. So it's um, a rate limiter provides a fair and reasonable use of resources capacity when they are shared among many users. So primarily, if I would say, if you're using an API, if you have ever made an API call, so any open source API call will have a, 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 a limit on the frequency of the API usage. So, let's say if a API can be called by a particular user only, maybe let's say 10 times a minute. So they, even if you are calling, let's say any, let's say Google Map API, you're trying to integrate that in your system, a Google Map API will have a limit on the number of times you can call that API. So if you are trying to call the API anything beyond that limit, it will just discard your request. So essentially, on the API side, they will be using a rate limiter which will manage the quota based on maybe a user ID or whatever their criteria is. In our case, let's say I gave the example of Google Maps. So it essentially throttles user based on the user ID. So if you try to go anywhere beyond that quota, it will just discard your request. These are the two important benefits of rate limiter. Then there is also, like, it also helps control the data flow. So if you have a large amount of data that you want to process, you want to use a rate limiter to basically evenly distribute it across machines and handle the data and process it in a distributed manner, and not have like just one single machine carrying all the burden. The last one is avoiding excess cost. It is similar to the first point. So if you also, every request that is sent to the system has a cost. So it has a database cost, it has a input output cost. So all of these cost, any request can be a costly operation. So to handle the overall cost of the system, we want to manage the number of requests any system can handle, so just to avoid any excess cost. So these are like the benefits of a rate limiter. Next, we will, this is a diagram that explains this, how a rate limiter works. So here you have a client side, you have a phone or a web application. You send a user request. Now, here, there's a client identifier builder which basically identifies the, let's say if you are throttling based on a user ID, it will help identify the user ID here. Now there is a decision maker. This is what is the rate limiter, which will basically tell the system to handle, to accept or reject the request. So this rate limiter has a rule here. So rule can be anything. If you want to limit the number of requests based on user ID, so here there, this will contain the rule that will say that for every user just allow 10 requests per minute, per minute or per second, whatever the rule is. So it will check the rule. Now this rule can be, if there are like a lot of different criteria of rules, user ID is just one such example. The rules can be based on, let's say, on a business level. If a business, if a Uber wants to integrate with the Google Maps, they will obviously have more quota than if an individual user wants to access it. So all of those different rules can be added, can be found here. It'll be stored in this database. So once the rule says that, the rule can basically say that let the request go through or discard the request. So now if it says that to accept the request, The request will further process, and it will reach the server, and the server will do whatever the request is supposed to do. Now, the other thing that the rate limiter can also discard the request. So if it says that reject the request, uh, there can be two things. So either we can discard the request altogether, which is this discarded request. So the API can either send like a 4429, which is too many requests, or a 503, which says that service unavailable. And there are more number of codes that will tell if a API request is declined, why it is declined. All these code will help explain the reason for the discard. Or if we don't want to discard, there can also it can also be stored in a queue. A queue will basically control the frequency of the usage. So if let's say 100 requests are sent at a time, only 10 went through, all these 90 will go here, and the 90 can be stored in the queue, and it can be processed a minute later. So once the 100 requests are processed for a minute, in the second minute we can handle 100 more of those requests, and so on. So queue basically serves as a storage mechanism. And why are we using a queue? So for queue is basically first in first out. So it helps us to process requests in the same order that they came in. So whatever is first in the queue, that will be processed first because that request came in first. So this is the overall architecture of rate limiter. We also have few rate limiting algorithms. There are a couple of algorithms. I will just discuss the two most common ones here. So first is the token bucket algorithm. So here, uh, the whole idea is there we will determine beforehand how many number of requests we want to handle. So here you can see there are this is a it's a bucket like architecture where you have a four tokens in the bucket. So the whole idea is whenever a request comes in, we check if there are sufficient number of tokens available. So once the first request comes in, we see that there are four tokens. Each of these token means that the request can go through. So we'll check if there are sufficient tokens available, we'll just take one token out of the bucket and the request will be processed. Now, once the first token is taken out, there are only three remaining in the bucket. That will mean that only three more requests can be processed. Again, when the second comes in, it will just take another token away. After that, there will be just two tokens remaining in the bucket. That will mean that only two more requests can be handled at that point of time. So this is how token system works. We also have something called we want to refill the tokens at a given frequency. So if we want to handle just four requests for every minute, so at the start of every minute we will have four tokens, and every request that comes in takes one token, processes that request. So once after the fourth request is completed, we will not have any token available here. So now what will happen is once at the end of the first minute, the tokens will be refilled. So all the four tokens will be added to the bucket. So at the start of the second minute, we will already have the new tokens added to the bucket. We will have fresh four tokens. Now again, the same thing can repeat. So based on the capacity of the system, based on the number of requests we want to handle, this is something that has to be determined beforehand. Like the capacity of the bucket will determine the number of requests we want to handle at a point of time, and same for the refilling. So how we want to refill the tokens, both of these numbers has to be predetermined. So this is it's again it's fairly simple and easy to understand. The next one is it's a bit modified to the token bucket algorithm. It's called the leaking bucket algorithm. It is Here what happens is it's same as like a water bucket. You have you have water filled in the bucket up to the brim. So any more water that you put into the bucket, the water will overflow. So exactly what is done here. So the size of the bucket here will determine the number of basically the capacity that the number of requests that the system can handle. So what we check here is the bucket full? If the bucket is full, yes, it will just drop the request. If the bucket is not full, add the request to the bucket. So the new request is being added to the bucket, and one by one, all the requests from the bucket is what is being fulfilled at that particular minute. So if the capacity of the bucket is 10, that will mean that 10 requests can be handled at in that minute. So once the capacity of the bucket becomes 10, no more requests can be put in the bucket. So again, all of these requests will be dropped. We also have an incoming request pipeline where all these requests keeps coming one by one, and pretty much so basically once the bucket overflows, any request will be declined. If we have space in the bucket, we can keep putting more requests, and one by one we will just process those requests. There is a question I see. Are the rate limiting algorithms hard coded, or are they like load balancing algorithms that are just selected? Um, there are, uh, I would say, there are 4 to 5 different types of rate limiting algorithms. So it depends on the system design. Ideally, these are predefined. So when we are designing the system, we will choose which algorithm works best for us, and that's how. So it will be predefined whichever. Let's say we pick the token bucket algorithm. The rate limiter will follow the same. It'll have like a fixed number of tokens, and only that number of tokens will determine what capacity is to be handled by the system. So it's pretty much predefined, and it's not selected on a random basis. It depends on whichever of the 5 algorithms suit best for the particular system. So these are the two primary algorithms. There are also more algorithms based on more algorithms for rate limiting, which we're just gonna cover these two right now. And the other ones, these are, I would say, these are the primary algorithms. The other are not so much important. So yeah, this is the whole idea of rate limiting. There's another question. Where do these rate limiting algorithms run on with regards to distributed systems, on the load balancer or one of the servers? So it runs here. So a rate limiter can be an individual, you can imagine it's an individual server. So you have the rest of the servers here. So this is one layer before the server. So this is the whole box that you see is the rate limiter. So even before reaching the server, the request first goes through the rate limiter. This will determine if yes, allow the request to go through, then it will go to the server and it will process the request as it is. If not, it will drop it. Uh, the next one is there's one more question. Just like how round robin and least connection are predefined for load balancer. Yeah. So the rate limiting algorithm will be predefined. Like yeah, it's also similar to an API gateway, which will determine has different set of rules which will determine how the API goes through. So this the idea is pretty much similar to that, but it is based on the different set of rules that we define in the system. And API gateway also does like more number of things. So you can imagine rate limiter to be like a subset of, like rate limiter does what like a subset of things what the API gateway does. Okay. Okay, if I let's move on to the next topic. It's called pub sub. Uh, it's Okay, there's one more question. Where does the rate limiter logic version control? So I showed that here. So here, this is the rate limiter. This, whenever there's a new request coming in, it checks all these rules are, there's a database that stores all these rules. So it will store, let's say for a user, allow only 10 requests to go through. So that will be stored here. If there is a business request, allow 1,000 requests to go through in a minute. So all of these rules will be stored here. So once a new request comes in, there is a logic that determines that first fetches the rule from the rule database, and that will determine if the request will go through or not. Okay. Okay, let's get started with PubSub. This is a very common uh, service being used in lot of messaging based system, lot of notification based system. It's the full form of PubSub is publish subscribe messaging. It's a asynchronous service to service communication method that's popular in serverless and microservices. So the next point is messages can be sent asynchronously to different subsystems of a system using a pub sub. So all these words, if you don't understand, I will first walk you through an example. So let's take an example of a WhatsApp group. So when you are messaging in a group, you have, let's say you have 100 people in the group. You sent a message in the group. Now all these 100 users have to be notified that there is a new message in the group. So if, let's say, if we just have one server, that if we have a logic that what it does is, let's say we have a new message come in and notify all the 100 users. So what can happen is, let's say out of the 100, there can be a possibility that a lot of users are not available at that time. Let's say they are offline, or for whatever reason, the notification does not go through. So if the server just sends the a notification request just once, what can happen is, let's say 50 out of those 100 users are offline, or whatever reason they cannot receive the notification. So only 50 user receive it, and rest of the 50 won't receive the notification anytime. So we don't want that to happen. So what usually happens is, once, let's say if you're offline, you come back online, you receive all the notifications at that moment once you become online. So how is that handled? So all of the requests, all these notification requests are sent to a pub subsystem. So what it does is, it has so the server does not send all the notification at once. Instead, there is something called a channel. So let's say if you have sent a message, there is a new channel created. You can imagine the channel to be something like a queue. So your message is added to the queue. Now all the other 100 users are called subscribers. So you are the publisher here who basically sends the message. There is a queue. Your message is added to the queue, and all these 100 people in the group are subscribed to the queue. So what happens is, now if the 50 are online, they will get the message at once, and other 50 which are not online, will the message will still be in the queue waiting for them to be online. So once the queue, let's say when a new user was offline for a certain time, they come back online, that's when they will be subscribed to the queue, and then they will fetch the message from the queue. So essentially there are like 100 different it's in the pub sub. There is a term called topic. So topic is, they use there are three different terminologies here. There's a publisher, there is a subscriber, there is a topic. So publisher is basically the person that the service that initiates the message. The consumer or the subscriber is the one that is the, so it's towards the end request, and anything in between is called a topic. So topic is something like a queue. So here all these subscriber will have their individual queue. So there'll be 100 queues. Your message is added to all these different queues, and whoever is online fetches the message in real time. Whichever is offline, the message will still remain in the queue. Whenever they come back online, they are able to pull the message from the queue. So in this architecture, whoever if a consumer is not able to get the message immediately, if they're offline, they won't lose the message. They will also get it's pretty much the same thing. Once you come back online, you will see like 100 of messages that was sent in last 1 hour when you were offline. So all of these will have like a separate queue for all the messages and the notification. And once you come back online, you pull everything from the queue. So let's look at the architecture here. So you see a producer. Producer is same as a publisher. You send a message. It's a pub sub system. Um, and then on the right, you have a consumer, also called a subscriber. So there are like here you have three consumers. So there are three queues. There are three separate queues. So you can see there are two types of messages. One, there are different colors that show like message coming from individual producers. So it goes through the pub sub system. It's added to the queue. The queue is also called topic. It's the terminology that is used here. So these consumer is subscribed to the queue, and whenever a new message comes in, it'll just be added to the queue, and it will be processed in the order that the request comes in. So it's here what happens in this kind of architecture, you also don't lose out on messages. So if you are offline for a long period of time, you're offline for a month, still all the requests will be um, just stored in the queue one after the other. Once you come back online, it can be just pulled, all the messages, all the notification will be just pulled from that queue. In case, I think there is also some like a time to live, which will basically determine um, the this it will basically determine the amount of time a particular request stays in the queue. So let's say if you are offline for a very long time, maybe your queue can no longer handle the number of messages or notifications in the queue. In that case, there might be a secondary storage or a database or a cache that will basically store all the message that are not being handled in the queue. In that case, the consumer will have to pull everything from the cache. But for a short time, this is what a message or a notification based system uses. So, yeah, this is the whole idea for a pub subsystem. Are there any questions with this? Okay, if no questions, I'll move on to the next topic. It's called Blob Store. Blob stands for Binary Large Object. It's a storage solution for unstructured data. So, what is unstructured here? We can store photos, audio, videos, binary, executable codes, or any multimedia. So, anything other than your the conventional data, basically anything other than text and numbers that can be stored in the form of a structure. All these unstructured data is stored in what is called a blob type of data. Uh, a, a blob consists of a collection of binary data stored in a single unit. So all of these unstructured data are stored in the form of a binary data. It's also an important component of many data-intensive applications such as YouTube, Netflix, Facebook. So you can imagine all of these applications have uh, a huge scale of unstructured data, photos, audios, videos, anything. So all of these are stored in a blob store. A blob store here can be anything. Either they can have in-house storage, or they can use a third party cloud storage to store all these blob storage. So it's mostly it's a third party cloud storage, because you can imagine the structured data, the unstructured data like a photo, video, audios can be memory intensive data. So cloud storage will provide a cost effective option to store all those data. So here I've just listed like few examples of blob storage which this applications use. Netflix uses a S3, Amazon S3, YouTube uses Google Cloud Storage, Facebook uses what is called the Tectonic. So these all of these are blob storage. This works pretty much similar to each other. Um, we'll have I'll explain a design, a high level design of the blob storage. So before let's first concentrate on the smaller part here. This is what is a blob storage. So here you can see there are multiple nodes here. These nodes are called like each of these nodes are also called a container. These containers are labeled according to the data that they are storing. So let's say one can be for image, one can be for video, other can be for audio, and so on. It's just to better structure the data. Um, this is what can be like a blob storage. There can also be a manager node. This node basically handles all the metadata. So metadata basically will contain anything related to the audio file. It can contain, let's say, if it's an audio file, it will just contain maybe the name of the file, the size of the file, the timestamp when the file was stored, and you can imagine any metadata related to the audio, video. All of those files can be stored here in the metadata database. There's also a monitoring service which will again do a continuous health check of the system to determine. It is similar to what we discussed earlier in the distributed caching. So this just monitors the health of that particular uh, basically it monitors the health of the entire blob storage and checks which is up and running. If something goes down, there will also be a backup of all these containers. So once if let's say a container is down, there will be a secondary container that will replace the primary one, meanwhile the primary is fixed. So this is the blob storage. The rest of the architecture is same. There is a client, there is a rate limiter, there is a load balancer, there is a front end server which sends the which determines which basically it does all the processing. Then it determines, let's say if I need to access audio data, then it will go to the blob storage, and then rest is pretty much same. There is also an admin which basically on a high level monitors, keep a check on everything that exists inside the blob storage. So yeah, this is the overall design. You can see all the pieces coming together. Earlier we discussed about the rate limiter. So we have a rate limiter here, then we have a load balancer and everything. So essentially, whenever you study all these individual topics in a system design, you have to see how all these pieces are coming together. And it's good to see when you're studying everything individually, it's good to see whatever you have learned coming all together. So we already learned about load balancer, rate limiter, servers. Now we learned about blob storage, so you can see how all of it came together. There are also a lot other blocks, but which are missing here. But still, you get an idea of what I'm talking about. So this is all about blob storage. I think this is the last topic. It is distributed logging. So why do we need logging? So if you write any small piece of code, we usually, if something goes wrong, we debug the code. So for debugging the code, what we do is we, let's say we add print statements to the code. Now the print statement will help us tell where exactly the failure is happening. So the idea is totally same here. So a log file records details of the events occurring in a software application. Log analysis helps to troubleshoot application nodes or network issues. So if anything goes down, the logs will tell us exactly where the failure has happened. To adhere to internal security policies, external regulation, or compliance. There can be, let's say, a compliance related issue, and this is the requests are dropping. So the logs will pretty much explain what's the reason behind a request that is not able to get through. To recognize and respond to data breaches and other security problems. Yeah, so once a request has come in, maybe the request went down. So the logs will also help us tell the reason behind why the request was not processed. The last one is to comprehend user actions for input to a recommender system. Yeah, so like a recommendation system, a user action can be logged. So whatever a user searches in a e-commerce, let's say, so it can be logged, and that will serve as an input to a recommendation system. So the overall idea is same as what we do in our day-to-day coding. So you add like a print statement that helps us determine where exactly the our piece of code is breaking. But if you imagine, if you just keep writing a print statement as and when your code scales, you just will lose track of everything. So once, let's say, you have 100 line of code, it becomes 1,000 line, it becomes 10,000 million lines of code. It will be difficult to manage if you just add like print statements in it. That's the reason you do something which is called as logging. You have like different levels of logging. This explains the severity of the situation. So here you can see there are 5 different types of logs. There is a debug, there is a info, there is a warning, error, critical log. So a debug log will it can be just for debugging purposes. So it can be anything like, let's say, in an API, you can add a debug log that pretty much anything that you want to log, which essentially does not uh, bring the system down, and it is just used for the purpose of basically maybe for a data collection or anything. It can be a debug log. There is the info log, which basically, if you, let's say, you want to print, you want to log something, let's say user location. If you're calling an API, the API wants to log the location from which the user is requesting the sending the request. So that would be termed as an info log. There can be a warning log. It might be a medium severe log where nothing is going down, but you want to warn that maybe, let's say, if your API is nearing the capacity, you want to send a warning log that will help log that you are very close to your capacity of your rate limiter. Then there is error and critical log, which, let's say, if the API is down altogether, so once you call the API, it'll just an error log that will say that the API is down, the request is not able to get through. So essentially, these logs, all of these logs, uh, uh, are stored in a server. So you can see on the right side, here there's a client, there's a load balancer, there is all these 3 servers. Each of these 3 server will log separately whatever is happening inside the server. All of these logs are collected. There's a log accumulator which accumulates all the logs. It can also do like a pre-processing that is required on the data depending upon how we want to store the data. Maybe it will just do a bit of structuring. And then there is it stores it in a blob storage. It can be not just blob storage. It can be any other. Let's say if you want to store it in any other relational or non-relational maybe database that suits your need, you can have that here. There's also an indexing and a visualization done on top of it. So you can't, if it's a large scale system, you can't just go and keep reading the logs one after the other, because it will be going in a it'll just start coming in a massive scale. So what you can do is you can visualize the logs. So you can have like a dashboard which will you can filter out the logs based on, you can just search for error log or a critical log, and it'll just show only those logs. So that will help you easily get to the root of the problem and understand if anything critical is happening. It'll be able to easily catch the problem. So that's the idea of indexer and visualizer. This is pretty much used, should be used in any system. Um, it is also a proactive mechanism to store whatever is going on in the system. And also, for the reliability of the system, uh, you want to be proactive and capture if the system has gone down. This will help us capture those requests. And you have a dashboard, so pretty much all these dashboards also have alerts sent to them. So any system will have the dashboards are automated. So if you can define that if it's an error or a critical warning, you can send out an email or send out an alert to whatever, let's say if there's an on call for the system, it'll send out the alerts to all these on calls. They can come in, they can check the dashboard, they can figure out. All these logs will also tell you where exactly the error is happening. So error log will also log let's say the error, the path, the file path from where the error is coming. So you can quickly go to the file, check that. It will also tell you the line number where the error is coming from. You can go there and see what is happening. This will help us to quickly locate the problem in the situation. So I think this was the last topic. Yeah, this was the last topic. We covered a lot of advanced topic, but still there are like lot many topics that exist inside. Lot many advanced topics that are there. Um, we can have like a separate session that will cover those topics, but this was all we were able to cover today. Let me check if there are any questions to post it in the chat. Um, is this called a high level architecture diagram? Yeah, this is a high level architecture diagram. So all of this diagram that I'm showing you, you should go and watch the second day's session. That's where we did like a high level design. So when yeah, when you are in a high level design interview, this is what is expected from you. You have to all the databases, the server, load balancer, caches, and whatever. These are like the primary blocks, but depending upon your system, you should add all these blocks and draw a high level architecture. Um, these things are, there's another question. These things are costly for business startups to implement. At what rate of active users, traffic requests do you start implementing rate limiters, distributed logging? So, yeah, it can be costly, but it is not just that it's costly. If you are growing in that scale, then only you need to implement. You need to understand the idea behind like a rate limiter. So rate limiter also helps control the cost of your system. So if it's a small startup, they, let's say they just have one database that handles all the requests, and that database can handle just, let's say, 10 or 100 requests per second. So it needs a rate limiter to make sure that the one database can handle all the requests that comes in. So even if, let's say, a startup does not have the cost for a, there are like a lot of third party solutions out there which maybe large scale companies do use. They don't build up their own rate limiter. They can also go to a third party rate limiter that provides the services at a cost. So either way, like there can be an in-house or there can be a third-party rate limiter, but pretty much all the system has to use a rate limiter to control the resource starvation. Um, okay, I think there's a question about a diagram. How are these diagrams done? I mean, which tool? Where do you get these images? I used So I have not drawn this diagram. I have sourced this from another place, but you can use. There are a lot of tools. I think. Uh, I think Figma uses. I have not used that for drawing the architecture diagram, but in an interview, you don't need this kind of fancy diagrams. There are like a common, like if you go to uh, if you are in an interview, whatever the mode in which the interview is done, let's say they are using a Google Doc or whatever they're using, you will have all these you can use like a basic symbol to represent all this, like a client, a server, a databases. So you can have you can learn about, I think there are very simple simple symbols that helps determine all these individual blocks. So you can just use that, and you can have an arrow between all those modules and determine the data flow. So it doesn't have to be this fancy. It is also not possible to draw a fancy diagram in a 45 or an hour long interview. So you don't have to worry about drawing a very fancy diagram. It can be a simple and easy block that shows, that explains what it's a database, or you can just draw a box and just label it as a database. That will also be enough. And you have to make sure the arrows and everything are particular, because the arrows helps determine the flow of the data. So that is very important. Otherwise, don't worry much about the making the diagram more fancy. Yeah, I don't see any more questions. I'll maybe wait for 1 more minute. If there are more questions, I'll answer that. We also have one more session in the pipeline, which will be next Saturday. That will be a very interesting session. We will have all these, whatever we learned in the past 4 session, it will come together. So all the high level, low level, and whatever we did today, we will we will take a problem, a real life problem of like a real life system, and we will go through. We'll start off with like the framework that we discussed in the first day, like how to approach the question, and then all the high level, low level, and advanced topic, all of this will come together, and we will basically see what exactly you have to do in an interview like setting. Can you share your LinkedIn? Yeah, I think I have it. Yeah, you can scan the barcode. This will take you to my LinkedIn. You can, if you have any questions, you can also reach me out there. I'll be happy to help you out. Can PubSub, there's one more question. Can PubSub be implemented for notifications alone? Notifications is one such example. There is also a lot of other use cases for a PubSub. So basically, you can understand whenever you just want to uh, have like a retry mechanism, you don't want to lose the request at once. Uh, a pub subsystem comes in handle where there are like multiple consumer of that particular message or a particular notification. You have to have like a pub sub architecture, so all of the consumer get the messages as they don't miss out on the messages, just to make the system more reliable. So this was just one such use case. But so the Facebook Messenger uses like a pub sub architecture. There are a lot other. I think WhatsApp also might be using something similar. So yeah, any messaging or notification based system uses, but there are also other use cases. It's not just limited to a notification system. Yeah, I think that's all the questions here. Thank you for attending the session. We'll end the session now. Do attend the last session that we have, which is next Saturday. It'll be an interesting session with a real question, real life system that we will talk about. Okay. Thank you, everyone. Thanks for attending the session.